All right, so today we are talking about more examples of related rate problems. So we've already learned this in the previous class, but we're going to look at different types and more examples and just try to become comfortable with it. So I encourage you to try this warm up on your own, and we'll go over it in class tomorrow, but just to read it with you, water pours into a fish tank at a rate of 3 feet cubed per minute. So feet cubed per minute is a rate at which the volume is changing. So just keep that in mind that this is dV over dt. And it says how fast is the water level rising? So think about which variable we would talk about in that case. If the base dimensions of the tank is a 2 foot by 3 foot rectangle. So if I draw this out, 2 feet, 3 feet. So there's your picture, there's your water, and it's rising. So think about that. See if you can do this on your own, and we'll go over the answers tomorrow in class. Okay. But just another reminder: dV over dt is volume, and we got a rectangular prism. So think about volume, rectangular prism. See if you can set that up. Okay, but the one that I really want to get to today is, I'd say, the third type of problem that we're dealing with related rates. So yesterday we did kind of the basic ones. The warm-up was kind of a basic one. And then we talked about ones where you have to substitute a value in, predominantly with like cone problems, maybe like that spherical problem was one of them. This last one is dealing with like an extra equation that I'd like to discuss. Dealing with distance and rate and time, something like that. Okay, so let's try this problem now. It says one train travels west towards Denver at 120 miles per hour, while a second train travels north away from Denver at 90 miles per hour. And thankfully that has already been drawn for us. So here's my central location is Denver right here at the axis. And it looks like that that one train is approaching Denver and one train is going away from Denver. At time t equals 0, the first train is 10 miles east, and the second train is 20 miles north. So let's kind of draw that out. So here we're 20 miles in the north direction and 10 miles in the east direction. Calculate the rate at which the distance between the train is changing at time equals 0 and then 10 minutes later. So that's the new part. Okay. Now, at time equals 0, this picture right here is already drawn at that exact moment of time. Remember, any picture we draw is at like a moment in time. In this case, at time equals 0. All right. So in this case, it wants us to calculate the rate at which the distance between the trains is changing. So it's asking us to figure out dz over dt. That's what it wants us to know. And in order to do that, I'm sure you noticed already the relationship between z, x, and y here. In this case, this is a right triangle. 3 sides of a right triangle, we're going to be doing the Pythagorean theorem. So before we do that, let's make sure we have all the missing pieces. So we need to know dz over dt. That's what we need to figure out. And all the other variables we need to know as well. In this case, there is no fixed constant. X is changing, y is changing, and the distance between them, z, is changing. So we need to figure out all of them and their rates. So thankfully, we already got what x equals and what y equals. And also, it told us in the problem what the rate at which x is changing is and the rate at which y is changing is. Now, this is another problem that I would like to address in these types of problems. Okay, whenever you're drawing this, like trains and whatever moving away and close to a point or whatever, whenever you're drawing it out, you always have a horizontal and vertical distance, x and y. Always have a reference, like origin. We'll call Denver, like think of it as the origin of a graph. And here's why. think of X and Y literally on a coordinate plane. Like if you're moving to the right, you're going in the positive direction. If you're moving to the left, you're going in the negative direction. Same thing for Y. If you're moving up, you're going in the positive direction. And if you're moving down, you're going in the negative direction. It's very important to keep that in mind so your signs will be correct. What I mean by that is if you look, this train is going 120 miles per hour, but it's going 120 miles per hour to the left, towards Denver. So it's going in the negative direction. So in this case, dx over dt is 120 miles per hour, but it's negative 120 miles per hour. And I promise you, if you draw a reference point, if you always treat left as negative and always treat down as negative, you'll always get the signs right. Okay? And in this case, you're going up, so dy over dt is going to be positive 90. Okay? And if the only other variable I'm missing is z here, if you want to find that, simply just do the Pythagorean theorem. 20 squared plus 10 squared equals z squared. And unfortunately, I don't think that's going to be a pretty number here, so we're going to keep it exact as much as we can. We're just going to say z is simply the square root of 500. Okay? Okay, great. So we got all the information we need. Now this is a lot like the problem from yesterday. So Pythagorean theorem. So we got x squared plus y squared equals z squared. All three variables are changing with respect to time t, so we can't plug in any constants. So we got the picture drawn. Now we're just going to take the derivative. Derivative is going to be 2x dx over dt, 2y dy over dt equals 2z dz over dt. Now let's plug in all the values that we know. We got 2, and then x is 10. dx over dt is negative 120. I get a question very similar to this on my written test, and you will be surprised at how many students get this question wrong because of that negative. They put 120 because it looks like it's supposed to be positive. It doesn't say it's negative, but we have to know that if it's going to the left or if it's going down, it's a negative direction. It just keeps all of our signs consistent. 2, and then y is 20, and dy over dt is 90. 2, all right, z is the square root of 500. And dz over dt is what I'm looking for. So if I were to solve this out, let's simplify this whole left side maybe. And I should have had it written out already. I apologize. I'm getting this to be 1200. And then we can divide by the square root of 500 times 2. So what we get is dz over dt equals, what's that, 600 over the square root of 500, which is approximately 26.833 miles per hour. So the rate at which they're changing from each other, all right, at time equals 0 is 26.833 miles per hour, which I think is pretty similar to what we did yesterday. We just found dz over dt. All right, here's where the new part comes into play. What about 10 minutes later? What about 10 minutes later? What's the rate at which they're changing distances from each other? Well, in order to do this, this picture drawn right here is no longer applicable. That is the picture at time equals 0. We need to have a new picture at time equals 10 minutes later. That's the new part, is redrawing the picture. Now just be careful though, because this is saying 10 minutes later, and everything else is in terms of hours, miles per hour, miles per hour, miles per hour. So we need to make sure our time units are always the same. And since we've already done everything in terms of hours, let's make sure that we rewrite 10 minutes in terms of hours. 10 minutes, 10 minutes out of 60 minutes, that's just the same thing as 1/6 hours. So that's the first thing we got to be careful of. 10 minutes later is a 1/6 hour later. Okay. Now, how do we redraw this picture? Okay. Well, it all comes from a formula we need to keep in mind, and this is kind of where I call the third category of related rates of changes. Third category is when we have to utilize distance equals rate times time. If I want to know how far that I've traveled, you're going to take your rate and multiply by the amount of time. For instance, if I want to know where my train on the horizontal axis is at, you're going to do 120 miles per hour times how long we've traveled. Well, we do 120 miles per every hour, and we've gone 1/6 hour. So, 120 times 1/6, and just be careful again because we are going to the left, so that should be negative. But what does that end up being? What's 1/6 of 120? It should just be 20, I think. Yeah. Negative 20. All right. Now, what that means is we've traveled negative 20 miles, meaning we've gone to the left 20 miles. All right, we have traveled to the left 20 miles. Now, remember where my original position was at. My original position was 10 to the right. If I subtract 20 from that, I am now 10 to the left. 10 minus 20 is negative 10. So I'm going to go down here. I'm going to redraw the picture. So I was somewhere over here. I was over here at 10. But then I subtracted 20, and now my new position is over here, especially if I keep calling this Denver in the middle. I'm now negative 10 away from that. I'm 10 to the left. This is where my other train's at. Okay. Now, what about that other train? So that other train was 20 above, right? It was 20 above, and it's continuing to go forward. Well, remember, distance equals rate times time. If I want to know how far I've traveled, the rate at which that other train was going, if you remember, was 90 miles per hour, and the amount of time that I've traveled was 1/6 hour. Which, if you do that, I think it's 15. Yep, 15. It means that that train has traveled 15 miles north. It keeps going north. So originally my position was at 20. I'm going to go 20 plus another 15 miles for a total of 35 miles. If I can draw that right thing. So if this is still Denver right here in the middle, this train has increased further up 15 extra miles, and this train has gone past Denver and to the left another 10 miles. So this is the new picture that we needed to draw. This is the picture, the snapshot that we're looking at now. And now everything goes back to the way it was. Okay? So I got x is equal to negative 10. And make sure you have it as negative 10. We're in the negative direction. Y is equal to 35. All right. Now we're going to figure out a new z value. And we're still looking for dz over dt. We're still looking at the rate at which the distance between them are changing. It just happens to be 10 minutes later. Dx over dt is still the same. It's still negative 120 miles per hour. And it's still the same for y. dy over dt is positive 90 miles per hour. Okay. So we got a new y, we got a new x. The rates are still the same. We just got to figure out our new z. And that's nothing too terrible. It's negative 10 squared plus 35 squared equals z squared. And again, I don't think this is the prettiest thing. I think z ends up being the square root of 1,325. Okay. All right. So now we can use our Pythagorean theorem, just like we did yesterday. I'm having trouble writing today. All right. So then it becomes 2x dx over dt plus 2y dy over dt and 2z dz over dt. It's something I should have said a long time ago. You can divide the 2 out. And some of y'all probably already did, but the 2 can go bye-bye. I don't need to keep multiplying everything by 2, so I can just divide it out. Maybe it makes our lives a little bit easier. All right. X is -10. Make sure the signs are correct. Denver is our reference point. We're to the left of that, so it's -10. And we're still going -120 miles per hour. Plus, y is now 35, and dy is still +90. In this case, z was the square root of 1,325, and we're looking for dz over dt. And just like before, if I were to solve this out, the whole left side becomes 4350, and we're going to divide by the square root of 1325, and that is approximately equal to 119.504 miles per hour. Makes sense to me that it's bigger than the last problem, because in the previous problem, this train is traveling towards Denver and this one's going away. So it's almost like, yeah, that train's going away, but this train's getting close to Denver. I don't see their distance going between them that much, that fast. But now the train is past Denver and is continuing going to the left, and this train is still going up. So their distance between them should be increasing a lot at a lot faster rate. Okay, 17 minutes in. I might do one more. This is a great problem that I may hold off on. Okay, yeah, I think I'm going to save this problem. I'm going to save this problem and number 6. I'm going to save this problem and this problem for tomorrow. I might do this problem. I might not. It's just a good extra problem. I definitely want to do example 4, and I definitely want to do this one with y'all in class. I wasn't going to do this on the video at all, because this is our first official free response question that we're going to do. It's from 1995, question number 5 on the AP response. So this is exciting. We get to finally do a question. All right, well, we'll just end the video. It's a shorter video today, only about 19 minutes, so that's good. Enjoy the other 10 minutes. Do whatever you need to do. You can try these other problems. And we'll pick it up back in class. So y'all have a great day. Talk to y'all then.